So I mean, as you noticed last week, I like geometrical concepts. So instead of just considering this problem here as just kind of a PDE by itself, I like to think about the solution manifold for the moment with some lambda fixed, and it's a nonlinear solution manifold, and so I like very much thinking in terms of kind of this geometry. I mean, be it the Wasserstein space or be it regularity structures. I think although it's kind of completely informal, or it's informal because it's infinite dimensional, it gives you the right idea and it kind of motivates very much what's happening or what should be done. So I'm going to continue to stress this, and in fact today we'll, in the context of the Malliavin derivative, we'll encounter the tangent space to that manifold. But so far what we have seen is that what we were interested in is to construct a parametrization of the solution manifold by, so this here is the solution manifold. Those here were the affine functions, spacetime, sorry, not affine, analytic spacetime functions. But then we realized what we constructed implicitly depended on the choice of the origin as the center of the world. And if we replace that, if we just followed the same rules but replace the origin by some other, let me say, base point x, so that's again the space of analytic functions, then we get, in fact, a different parametrization. And like in differential geometry or in differential topology, if you have more than one map, more than one chart, so when you speak of a chart, typically you turn this arrow around. So if you have more than one way of parameterizing this, you also have a transformation on parameter space, and that's what we were looking at. So in a certain sense, this here was algebraized by pi, this was algebraized by pi x, and this was algebraized by gamma x. And in the end, what was more important was the dual, because we had this relationship between the model in its original version, where we put the center of the world into the origin, and the model with another center. And by the way, this is what, so this collection of infinite hierarchies of random spacetime functions, which don't just depend on beta, but also depend on the base point x. This is what Heira calls the centered model. And this is really the geometrical picture. It provides a parametrization of the nonlinear solution manifold. So that's where we are. So there's always kind of a completely informal point of view, which is geometric, and then there is kind of the algebraic counterpart, which is which lives in these spaces of formal power series, and which is completely sound, and which is the level on which, in the end, the analysis and the estimates take place. But I think it's important to have both points of view in order to not get lost in combinatorics. Okay, so this is where we were, and I stated last time I stated the main result, but I skipped one chapter, so we are now in chapter 2, which is main result and sketch of proof. And I skipped the first section in that second chapter, which was entitled "What Estimates Can We Expect?" And I want to go back to this, and then in half an hour or so, or 20 minutes, start speaking about the Malliavin derivative. So, no, this is still pretty dark. So, now I forgot. I have to look up which sections, since I want to stick to my numbers, which section that was in. So we had a discussion in the first chapter, section 10, if I'm not mistaken, on so recall this section on scaling. In this section, we convinced ourselves that should we have a noise which has, like white noise, a nice invariance, scaling invariance in law. So that was S minus D over 2 psi. For us, capital D is equal to 6, so D over 2 is 3. But let's stick to the more general case. So if we had this type of scale invariance of law, then at least in the limit when we get the when we let the regularization go to 0, we should expect that our model also kind of inherits this scale invariance in law, and in the form of r to the power homogeneity of beta, and that was exactly the reason why we introduced the homogeneity, and the same is true for the pi minus. Just there, the scaling is worse by 2 digits, 2 being the order of the differential operator. And in fact, this it was convenient to rewrite this in a slightly different way. So we wrote that in the following way: the law of either r minus beta pi beta r 0 or r to the power 2 minus beta pi beta r minus 0 does not depend on r. And this kind of leads us to hope for, or expect, that even before letting rho go to 0, but uniformly in rho, we might have the estimate that the expectation of any algebraic moment of pi beta r 0, so that would be the pth moment to the power 1 over p, so that this is essentially a norm in probability space, the LP norm in probability space, that this is controlled by r to the homogeneity of beta, where the little r, I already introduced it here, was the mollification on parabolic scale little r, which we had defined earlier, and likewise for the pi minus beta r minus 0, which is worse. So if you look at the statement, or if you reconsider the statement of the main result, this is not quite the statement of the main result, because in the statement of the main result we were able to replace the origin, which is the base point of this model, by general point x, and of course that had an effect on the right-hand side. So, so this prediction is still somewhat impoverished. I like this word, impoverished prediction, because we want to be able to make a prediction on what happens if we replace this point 0 by general point x. And in fact, we do have the tools to make a kind of an educated guess what should happen in this case. So first of all, from the chapter, from the section where I told you, oh, unfortunately, we don't have a canonical parametrization, but for every base point x, we have a parametrization. From that section, which was section 13, we learned that or thanks to the assumption that our noise is shift invariant in law, remember that was the kind of very basic assumption we wanted to make right from the beginning. So thanks to this assumption, that translates to the model, but it translates to the model in this somewhat more general way that you have to shift both the active argument and the base point. Then this is has the same law as the original pi, and the same holds true for the pi minus. So this is almost tautological because changing, as I tried to explain, changing the base point means exactly following the same cooking rules to construct the pi x. So this should be true, just kind of as a general principle. And now that, of course, allows you to generalize this. So hence, we may upgrade the prediction star to the following. The expectation, the stochastic LP norm of pi x beta r at x is controlled by r beta, and the analogous condition for the pi minus. But of course, this is still impoverished, and it didn't gain as much because now still the base point and the active point are the same. Since the active variable is equal to the base point. So that didn't gain much. In a certain sense, it was too cheap. And now we really have to, in order to get a kind of better or finer or more precise prediction, we have now to invoke this object too. Let me do this. Because there is also, the structure suggests a scale invariance in law also of this object. And that's as follows. So I think I quickly plan to state that in section 19, where I said that the scale invariance in law of pi is consistent, and that's an easy argument which is in the script, is consistent with the following scale invariance in law of our change of base moment transformation, namely that this should scale in law like r beta minus gamma star x beta gamma. In view, and in order to see this, this is a component-wise statement. It's best to spell this identity out component-wise. So like a vector matrix multiplication. So pi beta is equal to the sum over all gamma of gamma star x beta gamma pi gamma. And I think I very briefly mentioned last time that these sums, although they look infinite because the set of all multi-indices is huge, I mean it's infinite in a very infinite way, although this sum looks infinite, it's effectively finite because pi x being an endomorphism of the dual space has the property that these entries, these matrix entries for fixed beta are non-zero only for a finite number of gammas. And I think we always arrange things so that you almost have the differential geometry summation convention that you sum over kind of similar indices if one's up and the other one's down, but I will always write the sum explicitly. So if you kind of combine the scale invariance we had on the p beta and of course also on the p gamma, you realize that this is consistent with the scale invariance of the transformation only if the scale invariance of the transformation is like this. So if you look at another base point and you look at how it transforms to the identity, you have to have this relationship. So that's a three-line explanation which is in the paper. Yes?
Sorry, in the last line I get there is an x for one of the pi's.
Yes, there is. Thank you. So that's just meant to be this identity, which here is an identity in the space X, Z3, Zn, to write this component-wise as an identity, identity between random space-time functions, which the components of the pi r, and of course also the components of the pi x. So, so that's the scale invariance that's consistent with what we have. So always in the limit, rho going to 0, and now this in turn leads you to conjecture the following estimate.
Sorry, but I have a question.
Yes?
Because you said it's a stochastic impedance, so I see an power 1 over p, so, but I do not.
Yeah, that's right. Yeah, I forgot the power p.
And could you kindly remind me what is the meaning of the gamma x star and then to the power of gamma on the left-hand side?
What is?
It's okay with that, but I mean, my next question is on your gamma, the operation gamma on the left. Yeah.
Left?
Would you kindly remind me what is the meaning of to the power of gamma?
No, that's just addressing the matrix components. So, so gamma x is an endomorphism, in fact, a random endomorphism of the pre-dual of our formal power series space, which is the polynomial space. And as such, we know that it has a matrix representation. And the matrix representation is what this is. And then, as you would do for the dual matrix, you would switch. So let me write it like this. You would switch the indices. So this is not a power. This is just referring, it's like when you have an endomorphism, even in finite space dimension, you have an endomorphism, which is an abstract linear map between, on a vector space. And then you have a basis on this vector space. You get a matrix representation. And now, I have, in a certain sense, an output index and an input index. So those are just indices and not powers.
Yeah, thank you.
Yeah. So that's just an index. Whereas this, of course, is a power. That's the pth power. So this is just the LP norm in probability. And that's the topology we will always consider. We'll take pth moments. We look at all the objects in terms of their LP powers. And if I write such a statement, it's always implicitly understood that it holds for all finite p. Right? And that the constants, in fact, depend on p. As you know, if you have a Gaussian random variable, it has Gaussian moments. So you know that the LP norms grow with a certain rate in p, I think square root of p. But then here we're, in a certain sense, looking at objects which are in a higher Wiener chaos. So those are squares, cubes, and so on of Gaussians. So they have a worse integrability. So, the square of a Gaussian just has exponential tails. But of course, all these objects, no matter how high a power you take of a Gaussian, it still has algebraic tails. And therefore, it's natural to always work with these norms as kind of norms in probability. More questions? Okay, so but I was in kind of I'm still trying to explain to you that the result I stated last time is, in a certain sense, the only natural result you can expect, and we're not yet quite there because. Yeah, right. Okay, so let me continue this line. So in view of this scale, so this is the scale invariance in law. The scale invariance in law of these change of the matrix entries of this change of base point transformation, which is consistent with the scaling in law of pi or its components. And now again, from this here, it's natural to expect the estimate that, again, looking at the same type of stochastic norm of a matrix entry of this transformation, that this one is estimated to a norm of x, a distance of x to the origin, to the power beta minus gamma, provided this norm is compatible with parabolic scaling So meaning it should be such that it should behave like this under parabolic scaling, and kind of a natural example would be the following norm. So it's not a norm, it's a distance function. You take the time-like variable, you square it, you take a fourth root, and then you take the Euclidean norm of the space-like variables and you square it. So that's a nice way of writing something which behaves like the square root of x0 plus the sum of the Euclidean norm plus the Euclidean norm and the space-like variable. And this is, for instance, I mean, there was one talk on sub-Riemannian geometry. There it would be called, and sometimes also in parabolic cases, it's called the Carnot. It's a kind of a very simple case of a Carnot-Kara-Theodori metric. And that's the meaning of this x, because that's kind of the way of measuring distances in time-space that's consistent with the parabolic scaling of time-space. And if we were to look at an elliptic, if L were an elliptic operator, we would take the plane Euclidean norm. And if L is some fourth order operator in space, first order in time, which is something a couple of people in Leipzig are looking into, then you would have to use yet another norm. So this norm here, the norm which you put on time-space is really dictated by the geometry of the differential operator. And that's one convenient choice. Okay, so that's what we expect, and this is exactly what we stated in the main theorem. That was the third point in the main theorem. So here we're happy. Here we're still impoverished. But now we have a way of combining these two things and get as a prediction the statement the statement we really prove. So let me show this. I need this identity. So I think today this is a bit too wet. So let's start from this here and let's mollify this identity. So let's apply mollify, which means we apply our convolution or mollification operator. And on the right-hand side, since this is not depending on the active variable, which in a certain sense is hidden here, the mollification operator pulls over this constant coefficient and ends up being just on the second function. And then, of course, we can also evaluate at x, which means we're evaluating at the point we're ultimately interested in, x, or on Friday some people prefer to call this y, but let me call it x, it doesn't matter. So the x ends up over there. Why am I doing this? Because now, here, I end up in a situation where I can apply this prediction, where base point and active point are the same point. So that's the merit of this transformation, that I can go from an active point, which is not the base point, to a situation where they agree. Yeah, that's just a little trick. And now I can take we apply our norm to this. We use the triangle inequality. Oops, now that one's lost. We use the triangle inequality and Hölder's inequality to get what? To get an estimate of the quantity we're interested in, which is the model where the base point, which here is the origin, and the active point disagree. And we get the sum over gamma of the 2p norm of the beta gamma 2p of the transformation times the 2p norm of the model at the base point x convolved evaluated at x, right? And that's a clean inequality which just follows from Hölder and triangle inequality. And now we can insert the two estimates we already believe in. So now we get the sum over all gamma for which I estimate this, that's here. So I get x to the power beta minus gamma. So now you see that it's important that I'm really, thinking of these estimates of being true for all p. Because now suddenly I have to use this estimate with p replaced by 2p. And of course, that will show up in the constant. The constant will become larger. It will be kind of, right, I will be using the constant here, which comes from 2p. And likewise, I will be doing this here. But since we don't care how the constants depend on p, I can be very sloppy here and just write it down. So we get r to the power gamma, right? And now this is in fact still a finite sum because most of these entries were 0. But now we need another piece of information which I stated, very briefly stated last time, which was the triangularity of gamma. And now I have to look up what the number was. Yes, 18. So now we need paragraph 18 from the last chapter, which stated that this here, or in fact something more precise, if we subtract the identity, that this is equal to 0 unless the homogeneity of gamma is strictly less than the homogeneity of beta. So that's a strict triangularity, which plays a major role in, which is part of the postulates of Heyre for regularity structures, and which plays a major role. And here you see the first time that it plays a role because it tells you that this here is non-negative. And since this is non-negative, you can do something very innocuous. You can add r plus x to the power beta minus gamma. So let me copy this again. So you get the sum over all homogeneities gamma which are less than beta. So there might be a number of multi-indices which have the same homogeneity. So I need to put a constant here, but that's a benign constant. Beta minus gamma r to the power gamma. And now there was, at some point, I told you that the homogeneity of a multi-index is never smaller than alpha, which, by the way, was a negative number. And because of these two bounds, you see that this is always less than r to the power alpha, r plus x to the power beta minus alpha. And that was what we stated. So I went through this one or two blackboards to tell you that the statement of the theorem is absolutely natural. You couldn't do anything else. It's the statement you're drawn to by taking invariances in law seriously and exploiting kind of the symmetries of the equation and the problem. So it's the only thing you can hope proving, and it's exactly what one can prove. Okay. Question. No, let me first start with the next section. Fine. So the theorem, perhaps I write it down again. So the theorem was the following. So suppose the ensemble of Schwarz distributions xi on R1 plus 4 has the invariances of shift and reflection, spatial reflection. It automatically has parity because I assume it's a Gaussian ensemble. For the moment, we can relax that later on. So it has these invariances, which were crucial, as I tried to explain, for having just the single counter term. So suppose we're in this situation, and we don't impose scaling because that might be too rigid, but we impose a bound as if we had a scaling. So we want to impose that that for all Schwarz functions zeta, so those are in a certain sense linear observables on which I can test my Schwarz distribution, and so that's a one-dimensional random variable, and I kind of postulate that the bound of this one-dimensional variable is estimated by the fractional h minus s norm squared of this Schwarz function. And if s is equal to 0, this would just be the L2 norm, and that would be, as an inequality, the identity you postulate on white noise. And now, as I explained, we in fact need to embed white noise into a larger class of noises, and because we need this s to be irrational. So for some s in 0, 1, irrational. So that it's strictly between 0, 1, where just the bounds, it shouldn't be 0 or less, because then the problem would not be renormalizable anymore. And it shouldn't be 1 or larger, because then the problem would not be singular anymore. And this irrationality was connected to the Liouville principle, which was crucial for our way of thinking, which makes the model kind of well-defined and unique. So those are the assumptions, and then the estimates are essentially already been on the blackboard, but let me copy them nonetheless. Pi beta r x p is estimated by r to the power alpha r plus x beta minus alpha. Note that this is always non-negative. If there is a minus here, then this deteriorates to alpha minus 2. And the estimate on on the gamma. And also this here is effectively always non-negative, because otherwise this matrix entry would vanish by strict diagonality. So besides the very first exponents here, which are negative, this is slightly negative, this is very negative, all the other exponents are positive. And the important thing is that the constants are independent on the regularization parameter. So in that sense, we can claim success that we achieved in constructing, at least in a term-by-term way, parametrizations of the solution manifold which stay controlled as the regularization parameter goes to 0, and which means, as these counter terms blow up. So in that sense, it's kind of the crucial result. Then there is, by Markus Tempelmeier, there's another result that in fact there is a unique limit, and that limit can be characterized in a suitable way via Malliavin derivatives, and I will get to Malliavin derivatives in a second. And so let me also say that these types of stochastics, so that's kind of what's called a stochastic model estimate, those were first proved in this context of regularity structures by A.J. Chandra and Martin Heira in I think a paper which was posted quite a while ago, which is not yet published. And it's kind of a monumental piece of work, which proceeds by completely different techniques. I mean, in a certain sense, it's much more general. They're looking at very general things, but it proceeds, it in a certain sense adapts the very graphical and combinatorial arguments via Feynman diagrams and so on from the math physics literature. And what we did is, at least in relevant examples, we gave a kind of completely different proof of these stochastic estimates, which are much more governed by this geometric thinking, and where the objects actually are also slightly different, because we're constructing actually a different model which is indexed not by trees but by these multi-indices beta. But from the analytical point of view, the main novelty we bring into this business is the Malliavin calculus, and that's what I want to explain next. But are there questions so far before I embark on the Malliavin calculus, on the statement, or where we're at, or why we're doing these things?
No, I don't know. It's just to check, what do you mean by underlining the exponent beta minus alpha and saying it's positive? You mean that we only state it for alpha such that?
No, while I didn't prove it, but the short proof is in the notes. These matrix entries are only non-zero if the homogeneity of beta is larger or equal to the homogeneity of gamma.
Yeah.
So in that sense, if you're in the opposite situation, the result is empty.
Okay.
So it's reasonable to think, effectively it makes a statement only in the situation when this combination, when this exponent is non-negative. And in fact, if this exponent is equal to 0, by the strict triangularity, in fact, this entry is just 1, and then it's also trivial. So I might even say this statement is only trivial when this non-trivial when this exponent is in fact strictly positive. But
as regards the condition of norm of beta minus alpha for the other equation?
Here?
Yeah.
So that was a property of, in the case we're looking at, so which was the case d is equal to 6 or little d is equal to 4, the formula for the homogeneity of a multi-index was this one here. And from this formula, since kind of the right-hand side obviously is non-negative, so alpha is between -1 and 0, you learn that the homogeneity of no matter what multi-index you take is always kind of larger than alpha. So here it's even simpler. This quantity is always larger or equal to 0, which is something I already used somewhere up here, I guess. Yes, I used it in kind of deriving this prediction.
Thank you.
More questions? Yes.
Some clarification on the notation for the theorem. Like you said that absolute x is the rectangular Taylor law.
Yes. So I will always use. You know, I mean, I have a couple of notational conventions which reflect the parabolic scaling without you know, putting an index. So for instance, when I address the length of a multi-index, a space-time multi-index, I always mean 2 times n0 plus n1 plus nd. And when I address kind of something which looks like the norm of a vector, I always mean what I wrote down. So x0 square plus the sum I d xi square squared 4th root. So, you know, in regularity structures, sometimes they would put an index s here for scaling, but I don't do that because I want to keep my notation lean. So whenever you see this here, it always means that and not the standard Euclidean case. And whenever you see this here, it always means that and not the standard definition. So that's actually, you know, quite important that, and we know that, I mean, PDE people know that a differential operator defines its own geometry. I mean, it's like in the sub-Riemannian case. You write down a differential operator, which is a degenerate drift diffusion operator, and it defines, in a certain sense, a strange geometry, which is, you know, this degenerate geometry in the sub-Riemannian case. Here we're not in the sub-Riemannian case, but in the parabolic case, but the philosophy is the same. A differential operator defines its own geometry. That's a very important principle in partial differential equations, that differential operators come with their intrinsic geometry. And whatever you do, no matter whether you define a Sobolev space, no matter whether you define a Hölder space, you always have to define it with respect to the intrinsic geometry. Now here I'm talking about geometry on space-time. More questions?
So following up on what you say, does that mean that if the L is not a heat operator, then?
Yeah, that's what I just, so if L, you know, the simplest case is L is the Laplace operator, then the 2 would drop out here, and this would drop out here. Yeah. So in that sense, so again, every differential operator comes with its geometry. And we're looking at the heat operator that comes with this geometry, and the Laplace operator would come with the standard Euclidean geometry. More questions? Yes?
So you're bounding the moments of these things.
Yes.
I don't understand how this fits into the scheme in general. Like, why isn't
Oh, there is this little post-processing, you know, by Kolmogorov. So, I mean, we like to call these here annealed estimates, because the norms we're taking is we take first a probabilistic norm and then a space-time norm. So we put the probabilistic norm inside. So let me use the language of annealed estimate. We coined that in the context of stochastic homogenization, where it was also very convenient. But then, as you know, with Kolmogorov criteria, you can always convert annealed estimates into quenched estimates, where you exchange the order, but then you lose a little bit of the exponent, right? That's the law of the iterated logarithm, even in case of Brownian motion. Annealed estimates of Brownian motion are simple. You get an exponent, the pristine exponent 1/2. But if you convert it into a quenched estimate, you have to pay with a double logarithm. So we don't do, we in a certain sense do that at the very end, because we want to keep our scaling laws clean, because you have seen that it's really scaling that, that determines everything and drives everything in our intuition. So therefore, we say this last step of converting annealed into quenched estimates, we leave it to the reader. More questions? What is the?
What is the variance bar, like the notation, long subscript h to the power?
Yeah. Okay. So I think I didn't specify this, so because that's in a similar spirit. So I don't know whether you've came across. So my short answer would be, despite this detail here, think at first of s equal to 0, and just think of me stating, you look at white noise. But then this is a little bit cheating, because you've seen that we need irrational. Okay, and there's this other issue. So as you know, kind of a Gaussian, saying that you want to consider a Gaussian is equivalent to saying you want to work with a certain Hilbert space. There's a one-to-one correspondence between Gaussians and Hilbert spaces. So now one has to be a little bit careful whether you want to think of the Hilbert space as the Cameron-Martin space or its dual, its L2 dual. That's something which sometimes gets a bit confusing. And both play a role because our random objects are not functions, but duals of functions, distributions. So in that sense, h dot minus s is the dual to the Cameron-Martin space of this noise. And the Cameron-Martin space is h dot s itself, but here I now have an estimate. So in this situation, so I could say EI Cameron-Martin space is stronger, is a subset of h dot s. So what I'm saying, if I'm saying that s is strictly larger than 0, I'm saying that my noise on small scales is more regular than white noise, which means I can test it against observables which are slightly more irregular than L2. That's the way how you should think about it, right? If you make this norm weaker, you make the norm in a certain sense stronger. You put more assumptions on the noise, on the noise. Yeah? So that's sometimes one has to be a bit careful with this primal dual. So by making this assumption, I'm relaxing white noise in two ways. First of all, I'm just requiring this inequality instead of an identity. And the second thing is I'm demanding these test functions, these observables, to be I'm allowing these observables to be in a larger space than L2. Yeah? Okay, now I have to tell you what this space is or what the norm is. So for me, a space is always the norm. Yeah, don't ask me to be too function analytic. So I give you what the norm is. So let's do it step by step, right? I mean, how would you define in the Euclidean case? How would you define in the Euclidean case the h dot 1 norm? You would say that's the following norm. You integrate, let's always look at the square. You integrate over space all the sum of the squares of the partial derivatives, right? That's the h1 norm. Yeah. That's, I don't know how familiar this is in this community. That's the notation for Sobolev spaces. Right? L2 based Sobolev space. It will never work with Sobolev spaces that are not L2 based. Okay, now how would you extend that if this index, which counts the number of derivatives, is not an integer? You would say, well, let's first write this here in Fourier space. So let's integrate over the dual space of a wave vectors Q, and let's use Plancherel, and with my physics convention, I think it would be this, and then you would have Q squared times the Fourier transform of zeta squared, where the Fourier transform of zeta for some wave vector Q is defined as, no, here I don't want to take it, and here I want to do the 2 pi to the power d of E I think people put a minus here, Q x dot zeta x, right? That's the definition of the Fourier transform, and this identity is Plancherel. Fourier analysis. And now you see that this one here is in fact a 2 times 1. And so therefore, the right way to define the dot always means homogeneous, which means I don't add the 0 order term, which is important. So S means that you stick to the Fourier transform side, and you define it as Q2S times F, or let me rather write it like Q times F zeta to the power S squared. Yeah, so this definition kind of contains that definition. That's the way how you extend it to fractional, so that's called fractional Sobolev spaces. And of course it makes sense for both for positive and negative S. So if S is negative, you're demanding more on large scales but less on small scales. If S is positive, it's the opposite. And but now, as you know, for us, it's not the Euclidean case that's relevant, but we need the parabolic case. And therefore, we have to do exactly this thing. So we have to replace this here, the Euclidean norm, by this norm, because that has the right scaling. Yeah? So that's what this norm means. More questions? Okay, so that's the theorem, and now I want to start telling you why using Malliavin calculus is a good idea in proving this theorem. So let me do it here. And I will take my excuses from Cefica and will use Malliavin calculus in a very kind of informal, sloppy, whatever name you want to say, in a very informal and sloppy way, right? I mean, this essentially what I'm trying to do is to give you an intuition about things and not to scare you with technical definitions. So what's a good way? So that's the section 4. So usage of Malliavin calculus. And in fact, it's just the first attempt. We have to then become more geometrical. So, how do I want to? So I want to have an informal view upon the Malliavin derivative. So let's. What's my? Malliavin derivative is you're given a random variable. But now, for a moment, think of a random variable as really nothing else than a functional or function of noise. So it's really something which takes noise in and spits out a number. That's a random variable. And the Malliavin derivative cum granum salis is of a random variable with respect to the noise is really very much like the Fréchet derivative. So if you consider it in direction of an element of the Cameron-Martin space, the good way to think about it, it's really, you look at your functional, you perturb the noise infinitesimally in this direction del psi, and then you take the derivative with respect to your t parameter, and then you evaluate at 0. So this is really how you should think, or how I would now like to think about the Malliavin derivative. Something really, at this stage, not completely subtle, nothing to be scared of. It's a direction. It's a Fréchet derivative, and in fact, I'm mostly interested in these directional Malliavin derivatives. And I will use the notation that I will call this del f. So del f is again a random variable, which is defined, or which you should think about like this. And now again, a big warning. I know that in Malliavin calculus, this del is used in the sense of divergence. That's not what I'm using here. I really use the del in this sense. So it's the infinitesimal, you perturb your noise in an infinitesimal way. No, it's like in calculus, right? You perturb your noise, or in applied math when you do a linearization. You perturb your noise in an infinitesimal way in some direction, del psi, which I always call del psi. And then you see what is the response you get. How does your quantity you're interested in, how does it change, right? Nothing deep. And there's something I wanted to say here. So, for instance, we want to apply this to the following random variables or observables. I'm using sometimes the probability language, sometimes the physics language. So essentially, what we want to apply this to is for instance, the random variable, which is given by taking the model. More interesting for us is the right-hand side. We look at a certain component, we convolve it, and we evaluate at a general point x. That's a typical example of a random variable we're interested in. Obviously, this somehow depends on the noise. Of course, in a very nonlinear and non-local, and in fact in a multilinear and non-local way, it depends on the noise, and we're interested in the noise sensitivity. So therefore, morally speaking, the Malliavin calculus probes or monitors how a solution phi of our PDE, which is parameterized by lambda and p, depends on the noise. by a linear analysis, by sensitivity analysis. So it's kind of some kind of sensitivity analysis. This is how you should think about the Malliavin derivative. And this is actually how we've used it in stochastic homogenization. It tells us how sensitively a solution, in this case of a nonlinear PDE, at some point after convolution, depends on changing the noisy part in your equation, which here is the right-hand side at some other point. Right? That's the kind of the best intuition I can give. So why is that a good idea? So let me recall what the challenge is. The challenge really resides in the relation between how to go from pi to pi minus. Let me write down this formula again. Or perhaps I do it because that's really a crucial point. I do it up here. So pi minus. So the adult version was Z3 pi cubed plus C times pi plus Xi times 1. And the down-to-earth version was this component version which I was about to write down. Where this is always the Konica symbol. So that's the spelled out version, right? And in the end, the model was defined by iteratively solving a linear equation and using this nonlinear function. So like often also in continuum mechanics, modeling is kind of a combination of linear relations, linear differential relations, and nonlinear pointwise relations. And that's the nonlinear pointwise relation. So the nonlinearity is here. And so what's the challenge? So number one challenge is, so what I want to claim is that this relationship is not stable or robust as rho goes to 0. Why is it not stable? Well, there's one easy way to see it. The one reason is what I always told you, although I never really kind of drove it home, but you should believe it to me, that these constants diverge. So this is an identity in which you cannot pass to the limit. So therefore, it's not stable, obviously, right? There's no way you could hope to ever write down this identity in the limit, very much like you cannot hope to write down the renormalized PDE in the limit. So that's the first conceptual problem. But then there is a more analytic or more down-to-earth problem, namely that these functions here have a regularity, or have order of regularity, alpha. So as rho goes to 0, the order of regularity is just alpha. Perhaps that's something which I actually didn't explain. I think I missed to make that remark of actually interpreting the result. Let me write down the result. R, X, P, in fact, to the power r, that was estimated by r to the power alpha, r plus x to the power beta minus alpha. And in fact, that's our result, and we think that this is sharp by paragraph 1. So if we believe that this is sharp, at least in the limit, if we believe that this is sharp, what does it tell us about the function? It tells us that if we take an arbitrary point and we mollify a little bit around this point, so now I'm thinking of small r, then this mollification in fact blows up like this power. Remember that alpha is negative. Alpha was 1 minus s, s minus 1. So the first piece of information we take out here is that in the limit rho goes to 0, kind of pi beta converge to a distribution, a genuine distribution of order alpha, which is negative. Okay, but then there are more information. So for instance, if x is close to the base point, the origin, then you get the benefit of the second term. So if x is equal to 0, then in fact you get the sum of these two exponents, and you see that pi beta vanishes to order homogeneity of beta, and that's a number which typically is much larger than alpha in x, in the origin, in the base point. And since this holds for small and large x, that's also the growth. So we get a pretty clear picture of how these functions look like. Schematically, so here is time space. Here's your origin, your base point, which here is equal to 0. They vanish potentially to a high order, but then they're still, extremely rough. Right? So there is, in a certain sense, a polynomial behavior, an underlying polynomial behavior, which is captured by the exponent beta, or a power law behavior, which is captured by the exponent beta. But then, superimposed on it, there's huge roughness. In fact, these things in the limit are not functions, but distributions. So they're characterized by these two features, roughness everywhere, but a certain vanishing order and a certain growth order at infinity. But so clearly, in the limit, those are just distributions. So that means I cannot take the product. So I still have the same problem. And of course, these two problems communicate with each other like they did for the original PDE. Right? Because that here is what comes from here, and the problem was this term. So there is a communication between these two problems. There are two sides of the same medal. And that tells us that this is not the right way to see, to understand the limit. So we have to find an alternative, and the kind of natural idea is to take the Malliavin derivative. So why is that good? Let me first say why it's good, and then let me perhaps tomorrow tell you why it's not that easy. So way out. Malliavin derivative. So why is it good? Why does it have potential? So the first observation is extremely trivial. So since the constants of the counter term C are postulated to be deterministic, of course, the Malliavin derivative vanishes. And in particular, the directional Malliavin derivatives vanish. So by applying the Malliavin derivative, there is a chance of killing these terms which blow up. In a certain sense, we look orthogonal. The idea is that there are certain, there are just finite directions in which this problem blows up. And by taking the Malliavin derivative, we kill these directions. We project on the orthogonal of these directions. That's the first obvious reason why you may want to take a Malliavin derivative, because you kill the divergent part, because the divergent part is only deterministic, which was the basic postulate on the counterterm. It should be a deterministic counterterm. Second point why it's good. Remember that somewhere last week I told you there was no reason to put more complicated counterterms like h rho phi square or h rho I di phi and so on. And I related that to what is called BPHZ choice of renormalization. And doing Malliavin calculus, in a certain sense, complements this in an almost ideal way, because, as you know, the Malliavin derivative of pi minus beta controls the fluctuations, or eventually, because we're going to use a spectral gap inequality, the variance of this random variable. Whereas the expectation, which is the missing part, is chosen in this BPHZ renormalization. So again, that's this idea that you separate your space of random variables into two parts, fluctuations and expectation, and you treat them very differently. And on the one hand, the Malliavin derivatives kills the expectation part, and on the other hand, it controls the remainder, the fluctuations. So therefore, that's the other reason why it's very natural. And the third reason is analytical, and has to do with the fact that you're making things more regular, because so taking the Malliavin derivative substitutes psi, the noise psi, which is of regularity s minus d over 2, which in our case is s minus 3, by an element of the Cameron-Martin space, which I always call del psi, which is in the Sobolev space h dot s. So there's a gain of 3 orders of derivatives. So it looks extremely good. At first glance, it looks like, you're surprised why people haven't done it before, because it looks extremely natural to the idea of renormalization. It's, in a certain sense, exactly looking in the orthogonal direction. It's killing the divergent terms. It's looking in the interesting directions, in directions where you kind of control, where you want to control something. And in addition, it improves the regularity by even the higher the dimension, the better the increase in regularity. So it looks like a very natural, and indeed it is a very natural idea. But now, so I'm not going to do this today. In kind of tomorrow at the beginning, I want to tell you, well, be careful. It's not that easy. And so, for instance, one technical reason why it's not that easy is that here you're comparing apples and pears, because when you say that white noise has regularity, or when you say that our noise has this regularity, you're thinking of, in a certain sense, a uniform statement because the noise is stationary, so it has this regularity everywhere. So this here is, in a certain sense, if you want C0 L infinity topology. Whereas we've seen that Malliavin, the Cameron-Martin space is always based on the L2 topology. So when we say that there is a gain of 3 derivatives, we're cheating ourselves a little bit, because in fact the two spaces have the same scaling, and we gain these 3 derivatives only because we look at a different topology, a non-uniform but an L2 topology. That will be a technical difficulty which one can deal with, but there are more serious difficulties here, and the easy one is to see that if you just hit this this identity with the directional Malliavin derivative, what do you get, right? I mean, so since the Malliavin derivative is a Malliavin derivative, I may use Leibniz rule, and what I get is using Leibniz rule, I get 3 times Z3 pi square plus C times del pi plus del psi times 1. Okay, so you first stare at here, and you like this because you replace the white noise, which is rough, by something which is better than L2. That's good. But then you look here and you realize you haven't thrown out the C. The C is still there. That's not surprising because the C is not showing up as an additive constant, but as a multiplicative constant. And therefore, if you apply Leibniz rule, product rule, that doesn't help you much. It's still there. So that's the first sign that you have to be smarter. And in fact, what I want to tell you next time is that the right way to get an idea of what to do is to actually think of the Malliavin derivative as being an element well approximated by the tangent space to your solution manifold. So I will, in order to overcome this difficulty, I will return to this geometric perspective which I've introduced last week of kind of a nonlinear manifold in its parameterization, and in fact will become even more differential geometry. I mean, again, on a completely informal level, will even become more differential geometric by thinking in terms of tangent spaces to this nonlinear solution manifold and representing the Malliavin derivative in terms of these tangent spaces. So that's for the rest of the week. And again, there should be a new version of the notes which already contains this discussion here. Sorry for being slightly over time. And I stop now. There's coffee, and of course there are also, if you have immediate questions, that's fine. Are there immediate questions? Yes.
Could you explain again what is called the S minus V over 2 equals S minus 3 means?
Okay, there was.
Equals 6, but I don't think we want that restriction.
Yes, there was one section, now I forgot which one, where I said I would like to restrict myself, for simplicity, I would like to restrict myself to this case. Because that, in a certain sense, from a physics point of view, that's perhaps the most interesting case because it corresponds to 4 dimensions in space, which is the dimension of Minkowski space. And that's what they're mostly interested in. But then it doesn't work for white noise. That's the famous result of Eisenman and Duménil-Coupin. But still, therefore, it's natural. I mean, I didn't find it a bad idea to focus on this case so that I don't have to, so that the formula for the homogeneity is pretty simple. So so indeed, I mean, at some point I restricted to little d is equal to 4, and therefore capital D, the effective dimension, which was always defined, 2 for time, 1 for each space dimension is equal to 6. In which case, the relevant range of S is strictly between 0 and 1.
The essence wouldn't change.
No, not at all. Not at all. Not at all. It's really just for convenience. More questions? I think then it's coffee time.